Okay, so the next topic that we're going to cover is the pathways of depolarization in the ventricle and on how they relate to the electrocardiogram. Now, before the 1950s, no one knew what the pathway of depolarization in the heart, and therefore the theoretical basis for what we saw on the electrocardiogram was not known. But Doctors Alan Shear and Alan Young were the first to map the depolarization of the ventricles. And what they discovered was the first section of the ventricle to be depolarized is here in the septal region when it has a mean axis or dipole axis pointing in this direction. Now, so you can take this little dipole and move it over here into this Einthoven triangle, and now you can project over, as we did earlier, what we would see as a voltage from these arrow, this vector onto leads 1, leads 2, and leads 3. And so if we project over onto lead 1, we would see that we would have an arrow pointing in this direction or a vector pointing in this direction, which means we are having a depolarization that's moving away from this positive terminal of our potentiometer. So we would be measuring a negative potential, which is shown here. So over here on this last column are the electrocardiograms corresponding to leads 1, 2, and 3. And so and this would be time on the x-axis and voltage here on the y-axis. So we'd have a negative potential associated with this initial depolarization in lead 1. In lead 2, we would also see that this arrow is pointing a little bit towards the negative terminal, so we'd have a slightly negative potential here. And on lead 3, we would have a positive potential, okay, because the arrow is pointing towards this positive terminal. So if we're looking at leads 1, 2, and 3, we would see a strong negative potential, not so negative potential, and a positive potential. And then what they found later was when the heart is in maximum depolarization mode, there is a wavefront of depolarization shown here by the difference between the dark blue and the light blue of depolarization moving in the direction of this arrow. So the mean dipole axis of depolarization would be pointed in this direction. It's large because it's a large amount of tissue. And then we move that into this Einthoven triangle. Here you see a positive potential. And so if we look over here at lead 1, we had a negative, but now suddenly it goes positive, shown here. And if we look at lead 2, we see that this arrow is as large as this one, as the mean axis of depolarization dipole, and that would be a large positive potential as well. And that's shown here. And over here on lead 3, this would also be a positive potential, but larger than the one we saw initially. So we would have another upward deflection here. So and this is what the electrocardiogram would look like at this particular time in the pathway of depolarization. And then if we look later, we would see that we have up in the upper right-hand corner a depolarization vector, because this is the base of the heart and this is the last part of the heart to depolarize. That's pointing in this direction. It's small. And if we move that into our Einthoven triangle and we project this vector onto leads 1, lead 2, and lead 3, what we see is in lead 1, we'll still have a positive potential, but it's going to be much less than the positive potential we saw on the last slide. And so it would be a positive potential measured here. In lead 2, we would have a slightly negative potential. The arrow is pointing towards the negative terminal of our voltmeter. So we'd have a slightly negative potential. And lead 3, we would have a negative potential pointing in this direction. And so that we'd be measuring a strong negative potential here. And then, of course, when the heart completely depolarized, there would be no vectors, there would be no electrical activity. And our electrocardiogram would look like this in lead 1, 2, and 3. So we would have a Q R wave, a Q R S, and a R S wave for our electrocardiogram. Now if we go further and try and see how this data is kind of analyzed, we see that there is something called the axial reference system, okay, and This reference system is a circle shown here, and in the heart is put in the middle of this circle is placed the heart, and extending out from this heart are vectors, okay, that intersect this circle at different degrees. And what it shows is that if we project onto this circle lead 1, that would be pointing in this direction, and we call this arbitrarily 0 degrees. Okay, and lead AVL, which is shown here, would be at minus 30 degrees, and lead 2 would be 60, AVF 90, and lead 3 with 120, and so on. And so what this circle shows is that mean vectors of depolarization that are normal occur within this blue range, okay? But if those vectors of dipole vectors of mean axis of depolarization are left shifted as shown here, then that means that you would look to see if these were some of the causes. It could be an inferior wall myocardial infarction, a left anterior wall fascicular block, and left ventricular hypertrophy. On the other hand, if we had a right axis deviation, we would have these other possibilities as problems that are causing it. All right, so let's move on now and take a look at the horizontal plane around the heart where we have these leads, chest leads, V1, V2, V3, V4, V5. These are around the chest, they're close to the heart, and they're measuring voltages that changes that take place in the horizontal plane. And up here is the horizontal, this is the horizontal plane shown here. This would be the cross section in that horizontal plane, and this would be lead 1, V1, and this would be V6. Now initially there is a net depolarization dipole in this direction, and so since this is positive, moving in this direction towards V1, we would expect to see a positive potential, which is shown here. And on V6, where this depolarization is moving away from V6, we would see a negative potential, which we do. And then in panel B, where the in a period of maximum depolarization, you would see an arrow pointing in this direction, mean axis of depolarization. And on V1, you would measure a negative potential because it's moving away from this terminal. And on this V6, we would see a positive potential. And on V1, where late in the depolarization, we would see a mean axis of depolarization in this direction. We would see on V1 a strong negative potential because it's moving away from it. It's moving towards V6, so we'd see a very positive potential. And then, of course, when everything is depolarized, then this is what we would have seen in our electrocardiogram for those chest leads. Here are all the chest leads shown here, and what's evident is that initially you have a strong S wave which decreases with time, and an R wave which increases with as you go from the right side of the heart towards the left side of the chest. And finally, let's take a look at the electrocardiogram and see what this tells us. Okay, so this is our standard 12-lead electrocardiogram. We have 1, 2, 3, 4 traces. Now the lower trace is what we call lead 2. It's recorded continuously throughout the electrocardiogram. The upper 3 leads are broken up into 4 sections. The first section corresponds to lead 1, 2, and 3 shown here. The second section corresponds to AVR, AVL, and AVF, and the last 2 sections correspond to the chest leads going from V1 to V6. So let's take a look at the R waves, which are shown here, and see if they look like what we think they should look like for an mean axis of depolarization of 45 degrees. Okay, in order to do that, let's go back and look at our axial reference system. Okay, so if that 45 degrees would be here, so we would have a mean axis of depolarization pointing in the direction intersecting the circle at 45 degrees. So we want to know what would we expect to see on leads 1 and lead 2. Okay, so this is lead 1, this is lead 2. So it would be intersecting at 45 degrees here. So if we take a line and drop it from 90 degrees to this intersect this point on the circle, we will have a vector showing a polarization pointing in this direction, which would be positive, rather large. But if we look at it compared to what we would see in lead 3, it would be 45 degrees would be here, and then if we dropped dropped a line 90 degrees to this point on the circle, we would see this would be a rather large vector. So we would expect to see upward deflections, positive depolarization, or upward deflections in the electrocardiogram. Lead 1 would be expected to be smaller than lead 2. And let's go and look at the electrocardiogram and see if that's what we see. And of course, that is what we see. You see lead 1 is smaller than lead 2. They're both positive deflections. And what about lead 3? It says that it is a positive deflection, but it's much smaller than lead 1 and lead 2. And is that what we would expect to see on those leads? Okay, here's our 45 degrees here. 45 degrees would be intersecting the circle here, and we want to know what it looks like on lead 3. Okay, so dropping a vertical 90 degree intersecting line to the 45 degree intercept here would give you a vector pointing in this direction, which would be a positive potential, but it would be small. And of course, if we go over here and look at our electrocardiogram, we see that to be the case. So what else do we see on the electrocardiogram? We see that we have a slight upward deflection shown here. Those are the P waves, and we said that they would be positive on all terminals from earlier discussion. And then we have our T waves, which are deflections upward, positive potentials. And the reason they look positive is because the pathway of depolarization in the repolarization in the ventricles is opposite the pathway of depolarization in the normal individual. Some of us, myself, have an inverted T wave. And then, of course, we can look at the AVR leads quickly, and we see that we would get a strong negative potential in AVR. And if we look at our electrocardiogram, our axial reference system, this is AVR, and at 45 degrees would be pointing in this direction. So that's the opposite direction of the AVR, so we'd expect to see a very strong negative potential. And in AVF, we see a rather large positive potential. And if we go back to our axial reference system, we see that we have AVF, we have a 45 degree mean axis, so that means we would have a rather large depolarization in the direction of AVF, which would give us a very positive potential. And if we look at AVL, you can see that this 45 degree mean axis would be almost at 90 degrees, so it would be slightly positive. So that would give us a positive potential on AVL, which is shown here, which would be rather small. Okay. Now, and we see that our T wave is the same polarity as our R wave, which goes along with the known properties of the depolarization of the heart, which is that the repolarization is taking place in the opposite direction as the depolarization. And if we look over to leads V1, V2, V3, V4, V5, V6, we can see from looking at our previous discussion that those waveforms on the V1 through V6 are the same as we saw here, and that's what we would expect to see. That's what we expect to see as shown on this 12-lead EKG, normal electrocardiogram. And with that, that will be the end of this introductory video on the electrocardiogram.